Welcome to MrCScience.com's video on chemical equilibrium. We're going to talk about reaction rates and something called equilibrium. Your book defines equilibrium when the forward reaction rate equals the reverse reaction rate. Well, that may not make a lot of sense to you yet. Let's take a look. Let's take an acid-base reaction. So let's take our hydrochloric acid and combine it with sodium hydroxide, a base. Remember, the hydrogen or the acid's going to donate a hydrogen, the base is going to accept it, so it's going to make water. That hydroxy is going to accept that hydrogen and a salt, in this case sodium chloride. This one's already what's the word I'm looking for? Well, it's already got the correct stoichiometric figures on it. So, okay, so now what we assume happens, or at least we assume so far in the book, is that all the hydrochloric acid will react with all the sodium hydroxide, or at least one of them will run out the limiting reactant, and we'll get our products. In reality, that's a little bit of a lie. Some reactions will do this, especially things like combustion reactions, things like that, where product can leave the scene. But if product stays together, what generally happens is once you start getting a lot of products, you'll start seeing the reverse reactions start occurring. And some of the water and sodium chloride will be forming to make hydrochloric acid and sodium hydroxide. Now actually this is a little oversimplification because we're using an acid and a base that is ionic. We're going to have ions to deal with, so this is oversimplification. But in reality what happens is we get a forward reaction going, and then we get a reverse reaction going. And you'll eventually hit a place of equilibrium where the rate for both of these reactions is exactly the same, so forward and back. So most reactions will have this in between for forward and back. Some reactions will go this way, and we'll find later when we calculate equilibrium constants that some reactions will be going the other way. Maybe they're written backwards. Okay, this can be shown as a graph. Let's see, can I draw a straight line here? Oh, that's bad. Let's just do freehand. So if we make a graph here, and on this side we have reaction rate, generally in molarity per second, and on this one we just have time traveling forward. So if we start our reaction, our forward reaction, so our reaction going this way, starts here. We've got all products, no reactants. So as we start getting reactants in the mix, it will dilute the reaction and the reaction will start slowing down. Now once you start gaining products, you can start having that reverse reaction begin to occur. So as products are gained, the speed of the reverse reaction occurs too. So the forward reaction slows down, the reverse reaction speeds up until they hit a point of equilibrium, where the forward and the reverse reactions are the same rate. At this point, you're going to have all the products that you can have and all the reactants that you can have, and you'll just stay at that state. Now this all depends upon a standard temperature, holding the temperature steady. We'll see later that temperature will affect reaction rate as well. Okay, we define equilibrium with the equilibrium constant, large K. Now let's say we have a reaction plus B gives us CC plus D. This is just a reaction. Here's our reactants, here's our products. The little smaller case letters stand for the stoichiometric figure in front of it. So reaction constant is defined as we take our concentrations of our products in molarity over the concentration of our reactants in molarity. These are, and this is a concentration at equilibrium. So once that rate is the same across, this concentration's at equilibrium. Now, the only other thing you have to take in mind then is the coefficients. So any stoichiometric coefficient like C here will be exponential for that molarity or that concentration, D, A, and B. We can use this formula to calculate the equilibrium constant for the reaction. You'll notice that if we use exponents here, your units are going to change. If all these exponents are 1, molarity will cancel out and you'll just have no units. But you can have molarity, molarity squared, you can have 1 over molarity, 1 over molarity squared, all that. So much like the last one you were working on, the units on this can change. So basically, let's just take a look at a quick problem on this. Okay, looking at the on your own problem here, we've got, here, let's scroll that down just a little bit, give us a little more room to work with. So we got the following reaction. We've got nitrogen up into gas reacting with hydrogen gas. Will give us ammonia. Also a gas. Okay, so this reaction, when it hits equilibrium, its reaction constant will be calculated by taking our products. So we got the concentration of NH3, and its stoichiometric figure is 2, so NH3 squared, that concentration, over the concentration of our reactant. So we got N2 gas, which just is 1, so we don't carry that through, times the concentration of H2 gas cubed. Okay, so let's look at what they give us in the book. So in the book they say that the concentration of, let's start with our product. The concentration of the product, the ammonia produced, is 2.28 molar. So we got that squared over, they give us a concentration of N2 gas of 0.242 molar times concentration of hydrogen gas, which is 0.468 molar. Oops, that looks really bad. Let's rewrite that. 468 molar. All that to the third power. Let's get rid of that highlight there. Okay, so if we calculate this out, let's pull up our calculator. So if we take our 2.28 times itself, or squared, we're going to get 5.2 if we round. The units here will be molarity squared over 0.242 molar times 0.468 cubed. So if we do clear, we go 0.468. I'm just going to multiply it out. 0.468 instead of trying to find my cube. Okay, comes to 0.103. 0.103. Is that right? Double check it. Yep. Okay. And our units here are going to be molarity cubed. So if we go back to this and we take our 5.2 divided by 0.242 divided by 0.103 we're going to get. Looks like 208, 209 equals 209. And our molarity, we've got 2 here. Those will cancel out with 2 of these, and we'll end up 1 over molarity squared. That's how you calculate reaction constant. Should be pretty straightforward. Now this assumes that the reaction has reached equilibrium and that the temperature stays the same. So this reaction constant is just for a certain temperature. Now this reaction constant can tell us something about the direction that the reaction is going to proceed. Let's scroll up a little bit here. So in reality, K is going to be equal to concentration of the products divided by the concentration of the reactants, to state it very simply. So if we have a large number, that means the concentration of the products is much greater than the concentration of the reactants. That means our arrow is going to be going this way. So a large K, so K is large, then we get that. If we have small, K equals, say our products, I'm just going to say prod over react. If this is larger than that, our K is going to be very small. K is less than 1, then our arrow is going to go the other direction. So if products and reactants are equal, K is about 1. So if they're about equal, then we're going to use our double arrow like that. So a large K means it's going to go towards the products. A very small K, much lesser than 1, is going to be towards the reactants. And if K is around 1, then it's going to be either or both directions. So the reaction will be about equal going both ways. Again, this relies on temperature being constant. So a couple other things to take into consideration for this. Solids. Solids are not used in this reaction, or in this, because you can't, first of all, you can't get a concentration of a solid in molarity. It's just not possible. But solids behave differently. As a product, they will precipitate out and not react very easily. And as a reactant, they're just there. So, so solids are ignored in this. That being said, liquids are ignored as well. Now, this is different. Remember, if we have, here, let's do this. Let's take, I can't think. CH3OH, I think that's methanol. If we take that as a liquid, oh, that's not a D, liquid, then it is not used. It again doesn't have a molarity. You can't have a concentration. You have so many moles per liter no matter what. Its concentration will never change. But if we take that CH3OH and we make it aqueous, so we dissolve it in water, or then in which case then the molarity can change and it's used. So solids and liquids are not used in the equilibrium constants calculation. Your book gets into using equilibrium constant to predict which direction a reaction is going to proceed. So assuming the reaction is not in equilibrium, if you know the equilibrium constant, you can calculate the equilibrium constant currently by plugging in whatever concentrations they give you. And depending on if it's lower or higher, that will tell you which direction it's going to go. So if K is too low, here, let's write it out here. So let's go back to our K equals concentration of products over concentration of reactants. So if they give you, say, at a certain point in the reaction, they give you molarity of both. If K now is less than the equilibrium constant, that means it has to get bigger. In order for it to get bigger, you have to either create more products or create less reactants. So that means if we have our reactants gives us products. So if we have to create more products, we're going to have to go that way. So that means it has to go towards the reactants. If K now is greater than K, that means that we have to get smaller. So we're going to have to increase the reactants. So it's going to proceed the other direction. The reason I don't spend a lot of time on this, the calculation's the same, and in reality, they really don't do this much. It's hard to take the concentration of products or reactants during a chemical reaction. So it's possible if it's slow enough and it's mixed well enough, but it's hard to do. So now let's talk about Le Chatelier's principle. Le Chatelier's principle states when a stress such as a change in concentration, pressure, or temperature is applied to an equilibrium, the reaction will shift in the way that relieves the stress and restores equilibrium. That's kind of a mouthful. Your book has a good graph on this though, so let's go ahead and draw that graph to kind of show what's going on. So let's go back to our reaction rate, molarity per second, and our time. And we've got our forward reaction starts going down. Our reverse reaction starts going up until they reach equilibrium. Once both reactions, so we'll call this forward, we'll call that reverse. Now, what happens if we suddenly add more reactants? So if we add more reactants, that's going to cause this reaction to jump up. So our reactants are going to go, so our forward reaction is going to start faster again. And then as we create more reactants, our backwards reaction is going to continue on, and it's going to find a new equilibrium base. So if we plus reactant, so if we add reactant, it's going to force it to go to a new equilibrium. So in which case, what you're kind of doing, if you look back here, if we take our K equals concentration of products over concentration of reactants. So, and then K will stay the same, remember, for all temperatures, even if we add more reactants. But if suddenly we increase the concentration of reactants, that's going to drop our K down. That means our K now is going to be less than our K, which means in order to get more products to go back to equilibrium, we're going to have to continue forward. So the forward rate's going to go way up, and then they'll find a new equilibrium based on the new concentrations. Now, not only will changing reactants affect this, but changing pressure. Now, pressure, let's take pressure will go to the side. So if you increase pressure, pressure will go to the side with the least amount of gases. So let's go back to our what was that one? Oh yeah, our N2 gas plus, what was it, 3H2 gas gives us 2NH3 gas. That's a 3. Okay, so if we increase pressure, if pressure goes up, now it's going to want to get smaller. Now these two gases take up more space than this one gas. So what's going to happen is it's going to push the reaction more towards the side with less gases so that it can occupy a smaller space. So increase pressure, assuming, when you increase pressure, you keep volume the same or even sometimes decrease volume. is how you increase pressure, but that will cause it to go that way. If we decrease pressure, now there will be more room, so to speak, and so it will go towards the side with more gases. So that's how pressure looks. This only affects gases. If the same number of gases are on each side, or if there are no gases, decreasing or increased pressure will have no effect on the reaction equilibrium constant. So that makes some sense. Le Chatelier's principle, like the equilibrium constant, ignores solids and liquids as a stress. So adding a solid or a liquid, again, doesn't change molarity, so it can't affect the reaction constant. So this takes us to temperature. Remember how I've been saying the whole time, temperature remains constant? Well, temperature can change in a reaction. If you remember back, exothermic reactions give off heat, they become hotter. Endothermic reactions absorb heat, they become cooler. Same type of thing goes on there, so almost every reaction is either exothermic or endothermic, just in different varieties. I don't know if there is a chemical reaction where the bond energies stay the same. If there is, they may not occur. So let's take an exothermic reaction. So let's say we have A plus B with its stoichiometric figures gives us C. Here, why don't we just do a real one, just for the fun of it. Let's take methane, and let's add oxygen to it. Gas, both gas. We know in this kind of combustion reaction, we will get carbon dioxide, a gas, and water vapor, a gas. So looking at this, first of all, Le Chatelier's principle, if we vary the pressure on this system, you notice it's got the same number of gases on each side, nothing will change. But varying the temperature, we know this is an exothermic reaction. So not only does it do this, but it also gives us kilojoules of energy off. So that energy, remember, can be part of this equation. So in this case, with an exothermic reaction, the energy is a product. So if we increase the temperature, thus increasing the available energies, we've actually increased the products. So if our K equals our products over our reactants, if we increase the products, well, we're going to increase our number, our K is going to go up. Our equilibrium constant will go up. Vice versa, if we decrease that, if we decrease the products, then our K will go down because this is a product. Energy is a product. In an endothermic reaction, same thing, but instead you're going to put your energy here and do the same thing. So temperature can be considered a product as an exothermic or endothermic reaction. Now, like I said, everything is pretty much exothermic or endothermic. You have to figure that out. Your book will tell you, so you don't have to just say, oh, I wonder if that's an exothermic or endothermic. But so temperature will affect the equilibrium constant. Okay. What the heck does that say? Oh, donates. Oops, I left this playing. I'll see if I can fix it later. That's the end of ours. I'll work on a second video for the remainder of the module. If you have any questions, give me a drop me a line at mrc@mrcscience.com. Thank you.